Okay. Okay. Today we will start with some lectures about laser interferometry. And okay, what is laser interferometry? You already seen something of interference because you have studied the Fabry-Perot interferometer, that is also called the Fabry-Perot interferometer. Okay, so you have already seen something. And why you have already seen something? Because when we can talk of interference or interferometry, the principle is very simple. Okay, you will just need a single mode laser source. When I say single mode, I mean single longitudinal mode. Okay, we have an unperturbed electric field. This is the electric field that is emitted in continuous wave from the laser source. Then you can have a situation like this. This is a working principle setup, okay, not a real life setup, but can explain very easily what happened. So what you do, you split the beam into two beams, one that is called the measuring field and one that is called the reference field, okay? Then you can have, for example, two mirrors. You just reflect the measuring field back to this beam splitter, to a second beam splitter, where you recombine the electric field, reference electric field, and the measuring electric field. Okay, so here you have E1 that is given by the summation of these two fields. So when you have summation of two different fields that have different optical paths, you have interference. And this is the reason why you have interference also in the Fabry-Perot interferometer, because at the exit interface you have an infinite summation of contribution and electric field with different optical phase. Okay? The electric field works, the Fabry-Perot interferometer works because of interference. Okay? So now, let's introduce two quantities that are very important with interferometer. Let's call the reference path, that in this case is given just by this distance or length. And then you have a measuring path that is given by 2 times L2 plus L3. Okay? This is this path. Okay? So these are the bases. Now, let's start to move something. Okay? Let's suppose that these two mirror forms an object or a target that can move in these directions. Okay? So now what do you think that happened here? Because you know that if you look just at the electric field, you cannot see anything, because you cannot resolve optical phase difference with your eyes. Then you have to use a photodiode, okay? And if this object is moving or moves, then on the photodetected current you see something very interesting. That is very interesting. Why you see something that is interesting? Simply because the photodetected current is related to the optical power, not to the electric field. Okay? So it is related to the modulus, to the square value of the modulus of the incoming electric field. Okay? So if you do some math, what happens? Then the photodetected current is proportional. Okay. La batteria. Okay, there's a problem with the battery. Sorry for this. Okay, problem solved. Then you can introduce two optical phase. One that is related to the reference path, k is the wave vector, or the wave number, and the other one that is related to the measuring path. Now, in this case, we have a fixed, let's say, path that is given from L2 2 times plus L3. Then you have a time-depending path that is given by this displacement. Okay? So the object can move with respect to the starting position. Okay? And so what does it mean? That now the photodetected current is not a constant value that it should have been if you have just revealed or detected the unperturbed electric field zero, it's zero. Okay? So it's not constant. Or well, better, if this displacement is not constant, or even better to say, the object is moving, then you have that the photodetected current became something like this. Okay? Now, how much is modulated the DC value depends on the power reflectivity of the beam splitter. Okay? And it's just related to that. And now, let's start to talk of what is the value of displacement of the object that gives to you a phase difference of 2 pi. This say, in other words, how much I have to move to have a phase difference between the measuring phase, or the phase that is related to the measuring path, and the reference phase, that is the phase that is related to the reference path, in order to have a phase difference of 2 pi. This is the idea. And well, the answer is very easy, because now the phase difference, the phi is equal to, let's put it in this way, 2 pi over lambda, that is the wave vector, multiplied by Sm minus Sr, plus 2 pi over lambda multiplied by St. Okay, I can write it in this way. This is a constant term. It is not important. Okay, we can put this to 0. No problem. So what happens? That now we have to understand what is the value of displacement of this object to have a phase difference of 2 pi. So we can write this in this way. Let's call it ds or dst. Okay? And we want to equal this quantity to 2 pi. What you see is something that is very interesting, because now dst is equal to lambda. Okay? So if this object moves of a quantity that is equal to the wavelength of the laser source, you see onto the photodetected current a 2 pi phase difference. That, what does it mean? That you go from a maximum, then you have a minimum, and then you go back to a maximum. Okay? In your opinion, why this is a cool specification of a setup that is really simple? Because you just need what? A source, some beam splitter, some mirror, and a photodetector. Nothing more. Very easy setup. And you get an instrument that is able to measure displacement, incremental displacement, with a resolution of that is equal to the wavelength. Okay, and this is very cool. Why? Because the wavelength, when you talk of visible laser, is very short. We talk of hundreds of nanometers. So the resolution is very high, very good quality. And also there is another point that is very important, because now let's say the unity of measure is the wavelength, and now the wavelength is known with very high accuracy. You can go to 10 to minus 5, for example, when we talk of this quantity. So how much good we know the wavelength, we can go from 10 to minus 5 with semiconductor laser to 10 to minus 10 with TNE laser, very highly stabilized TNE laser. Okay, so the unit of measure is known with very high accuracy. And the wavelength itself is a very low value, so the resolution is very high. Now, how can you start to try to use this feature of the interferometer that we have developed so far? Because since you know that for each for each wavelength displacement of the object, let's say here we have the photodetected current, okay? This is the mean value. Let's suppose for simplicity that the reflection, the power reflectivity of the mirror and the splitter are so that we have full modulation of the DC value. Then you can just have something like this. You use a discriminator, okay, that sets, let's say these are volts, let's suppose, that sets a value of V0 when the photodetected current is higher than the DC value. So you produce a squared wave starting from a sinusoidal wave. Then it is 0 when the photodetected current is lower than DC value, and so on. Okay. And so on. Okay. Now, if you do something more, so if you do, of course, here we have time. Okay. Because recall that this quantity, this is the phase difference, can be also related to time, because never forget that this quantity, phi con m minus phi con r, is equal to this quantity. So you have time. Now, if you do the derivative of this squared wave, what you get? You get positive jump and negative jump. Positive, negative, positive, and so on. So this is the derivative with respect to time. Okay? So now, if you are able to count only the positive jump, you are counting jump each 2 pi phase difference, because this is the important thing. Each positive jump occurs for a phase difference equal to 2 pi. So if you count this jump, you already have an instrument that is able to measure the displacement of the target with a resolution that is equal to the wavelength. Okay? Very easy way, very easy approach. And since you have also the negative ones, you think that you go even better? You can do something better? Yes, you can do something better, because if you send this signal to a rectifier so that also the negative jump became positive, so if you do something like this, you consider also the negative one because they are rectified, okay, and you are able to count all the positive jump. Now the resolution, in your opinion, became
2 times
half of the wavelength. So you have doubled immediately the resolution of the instrument. This is a very, a very important quality, because I repeat this. The principle is very simple, and also the setup. You can do this experiment in a laboratory without too much difficulties, right? You can try to produce an instrument like this that is able to do this. It's not difficult. But the quality of this instrument is very high, especially because you can measure displacement with wavelength resolution. And again, I will repeat this, the accuracy with which you know the wavelength, that is the unit of measure, is very high. Can be very high. Okay, so this is a very good starting point. Then, some definition, okay? Usually, when you have a situation like this. You go from a maximum to another maximum, so you have this 2 pi difference in phase. You define this as a fringe of interference. We will see with a video something that is more clear, okay? Okay, and this is usually a definition, okay? When we talk of fringes, we talk of phase difference that are equal to 2 pi. For example, let's go back with a situation in which we are able to count also the negative pulses. This phase difference is pi, not 2 pi. So this is not a phase difference related to an optical fringes or a fringes of interference. Okay? Okay, good. There is also another very high quality or high feature of an interferometer because, as you have seen at the beginning, you start from a single mode laser, and then you have the recombination of the two parts of field that comes from the same optical frequency. Okay? So here you have a system that is equivalent to a homodyne detection scheme. Okay? And so a homodyne coherent detection scheme has another very important feature that is always possible to work at the quantum limit regime of detection. Now, do you know what is a quantum limit regime of detection? Okay? No? So we will review this. It's a very high feature, it's a very good feature because when you work at the quantum limit, the signal to noise ratio depends only on the signal properties and not on the photodetecting setup properties. Now, I hope it will be clearer in a minute. Because whatever is the photodetector that you are using, photodiode, photomultiplicator, and so on, and whatever is the electronic circuit that you use to amplify or to detect signal, you can always go to this simplified scheme. For example, here you have the photodetector, okay, and then you have an equivalent resistance, that is the input resistance of your electronic circuit. You can always go to this situation, okay? So what do you have? You have two contribution of current because you have the photodetected current, okay? But you have also the dark current of the device. So you know that for each photodetector that you use, you have a current even if you don't have light. And so this is called the dark current. And this is, as I said before, the input resistance or the equivalent resistance of your circuit. So now if you, this can be a power supply value, okay, that is higher than 0. Nothing more. So now if you look at the noise of this system, you have three contributions, okay? You have one that is related to the thermal noise, or the noise that is related to the resistance. This is given by 4 kB T B divided by the value of the resistance. Now, kB is the Boltzmann constant. T is the temperature in Kelvin degrees, and B is the bandwidth of observation of the phenomenon. Okay? This is called the thermal noise. Then you have two contributions that are related to the current, and they are called the shot noise contribution. One is related to the dark current, and this is 2. Let's use Q, ED, B, where Q is the electron charge. Okay. Again, B is the bandwidth of observation. And then you have the third contribution that is given by the signal, what you do, the signal that you detect. Again, 2Q EPH multiplied by B. Okay? Okay. Now, if you try to evaluate the full noise, or better say, let's evaluate the signal to noise ratio. Since I'm using variance, I'm using the signal to noise ratio squared. Okay. What does it mean? That the signal is EPH squared, because EPH is what is useful for me. Okay. And then I have to sum up this three quantity. I can, okay. EV plus EPH. Okay. Now you can have two situations. One in which the contribution of noise of the signal is higher, greatly higher, one order of magnitude, when you have this equality, of the other two contributions. So, the one that is related to the dark current, and the one that is related to the equivalent resistance. Okay? If this happens, you are in a quantum regime limit of detection. And if this holds, you have that the signal to noise ratio square of the, let's say, quantum regime of detection is simply given by EPH squared over 2Q EPH B. And so the signal to noise ratio depends only on the signal and not on the characteristic of the photodetector and the electronic circuit. This is a very good quality because you can think of signal to noise ratio without knowing exactly how it is built, the detecting scheme, and what is the photodetector. This is a very high quality, high feature of an interferometric scheme. And this is just simply related to the fact that you have a summation of two fields. Okay? If you work on the amplitude of the reference field, you can go in this situation. Okay? Always. And, of course, opposite, let's say, to the situation in which this, let's write it in this way. So this is quantum regime. Okay, and then you have when the opposite holds, so when you have that sigma squared EPH is lower, much lower than the other two contributions, then you say that you work in the thermal regime of detection. And in this case, of course, the signal to noise ratio depends on everything. Okay? Because now it depends, of course, on the signal. Sorry. Okay? But this quantity is cancelled out, and so it depends on the particular device and photodetector that you are using. Because now you have an equivalent plus the dark. So this is the thermal regime of detection. Okay? This is just a review. The important thing is that with this scheme you can always go working on the amplitude of the reference field, you can always work at the quantum limit regime of detection. Okay? Okay, you can go on. And so, very, very simple principle, working principle, but an infinite number of applications. In particular, we will see, this is the tree of laser interferometry. You can have application of interference in optics, electronic, mesoscience, wave and field, and technology, more generally. And then you have a great application. We will not be able to talk about gyroscope, ring laser gyro and fiber optic gyroscope. We will not be able, but anyway, this is a very, very great success of optical instrumentation, because you know that in each airplane, each ship, everything that moves has 3 gyroscopes. And if you think that a gyroscope of that kind can cost some 100,000 of euros or dollars, then you know that this is a very great success from optical instrumentation. Okay, we will not deal with this because of time, because you need time to talk very in a good way of gyroscope. Then we will deal instead with gravitational antennas or gravitational waves of observatory, especially because now, last year, they have detected gravitational waves, so this is good. I've done this seminar for 10 years, and all the years I said, oh, okay, let's next year probably they will detect something, and now they detect a lot of gravitational phenomena. So this is a very good point, even because this is I believe to say that this is the highest challenging instrument that is ever built on Earth. And in particular, its sensitivity. So the sensitivity means the displacement that is able to measure is the lowest thing that is possible to measure on Earth. Nothing is more lower than that. And you can also measure another multitude of things with laser interferometry. We will deal also with the speckle pattern. I don't know if with electronic speckle pattern interferometry, but sure we will deal with the single speckle. So we will talk also of this particular thing or branch of laser interferometry. Okay, so very easy principle, but an infinite number of applications. Now, these are the 3 most used interferometric schemes. These are the Michelson interferometer, the Mach-Zehnder interferometer, and the Sagnac interferometer. Okay, we will talk of the Michelson in all these lectures. So this is the most commonly used. Just to say 2 words on the Mach-Zehnder interferometer. Now, the difference between the principal scheme that I have shown to you in the first slide is quite easy, because you have, again, one laser source, then you have a splitter, you split the field into a reference one. The reference field goes in this path, along this path, and the measuring field goes in this path. Now, these 2 mirrors are fixed, so you cannot move this with respect to the other, okay? But you can change the optical length, because you can insert here a device that changes, for example, its refractive index by pressure, for example, okay? The more you press, the more you have changes in the refractive index. So what does it mean? That the optical length here changes, and so you have a measuring phase that is different from the reference phase. And so again, here you have recombination of the 2 fields, then you can use these 2 photodetectors to detect this phase difference, okay? And instead, the Sagnac interferometer is the one that is used in the gyroscope, okay? Or in the, yes, in the gyroscope. Now, what you see, you have again one single laser, a single mode laser. Then you have again the splitting of the electric field into 2 fields. Now, the 2 fields do something that is close to what happens in the Mach-Zehnder. The only difference is that one is clockwise propagating and the other is counterclockwise propagating. So, in principle, the 2 fields sees the same path. because both goes into the measurement device. The difference is that if this setup is moved, then you have an optical phase that goes between the clockwise and the counterclockwise electric field. This is a bit difficult to understand, but in principle, this is what happened. Okay? We have two counter-propagating fields, and then if this is moved or rotated, then you have an optical phase difference. And so, again, when you recombine the two fields, and you see the photodetected current, you can see the development of the fringes of interference. Okay?